Good afternoon and welcome to NASA headquarters in Washington, D.C. I'm Steve Cole with the Office of Communications. We're here today to give you a preview of NASA's next mission to continue our exploration of the solar system and specifically our sun. The mission is IRIS, and it will provide the most detailed look ever of the sun's lower atmosphere, a region called the interface region. IRIS, which stands for the Interface Region Imaging Spectrograph, is scheduled to launch June 26th from Vandenberg Air Force Base in California. We have 4 panelists today to tell you about the mission. First will be Jeffrey Newmark, who is the IRIS Program Scientist at NASA headquarters, Alan Teitel, IRIS Principal Investigator from Lockheed Martin's Advanced Technology Center in Palo Alto, California, Gary Kushner, IRIS Project Manager at Lockheed Martin's Advanced Technology Center, and John Marmee, IRIS Assistant Project Manager at NASA's Ames Research Center in California. After our panelists' presentations, we'll take questions from reporters on the phone lines, in the audience, and also those watching online. If you'd like to ask a question online on Twitter, please use the hashtag AskNASA. We have a lot more information online as well about the mission, and you can see that at www.nasa.gov/IRIS. We'll continue coverage of the mission up through launch at that website. So, to begin, we'll start our first presentation from Jeffrey Newmark.
Thanks. I'm thrilled to be here today to discuss the IRIS mission. IRIS is our newest member of our Heliophysics fleet of spacecraft. I'd like to start by giving a little background on what heliophysics is. We're both the oldest known science. People have wondered about the sun ever since we existed. And also we're new science, trying to understand the sun and its interactions with the Earth and the solar system. The domain of heliophysics ranges from the interior of the sun through its solar active atmosphere to the near space environment of the Earth and to the edges of our solar system far beyond Pluto. This whole vast extended region is the extended atmosphere of the sun. We call it the heliosphere. Heliophysics seeks to understand basic questions about this system, such as what causes the sun to vary, how do the Earth and the heliosphere respond, what are the impacts to humanity on the Earth and to other worlds as we explore beyond. In order to answer these questions, we use a fleet of spacecraft. We call it the Heliophysics System Observatory, or HSO. If you can show graphic number 1, please. The HSO utilizes our entire fleet of 18 missions over 28 spacecraft as a distributed observatory to discover the multiple scales and the coupled processes that work throughout this heliosphere and through this complex system that make up our space environment. Our spacecraft orbit the sun, the Earth, the regions in between, and out to the edge of the solar system. IRIS joins this fleet as the newest member of our Explorer class of missions. If you can please show graphic number 2. The Explorer program is the oldest continuous program within NASA. Explorers are one of the 3 flight programs we have in heliophysics. The Explorers offer world-class science with frequent opportunities at relatively modest cost. This brief montage that you're seeing here shows some examples of Explorer missions throughout the years, starting with Explorer 1, launched in 1958, the very first NASA mission, through some of the early explorers, to the Nobel Prize-winning COBE, to our more recent heliophysics explorers like AIM, RESI, IBEX, and of course, coming up to IRIS, our soon-to-be-launched Explorer. Although we already have some solar observatories in our fleet, IRIS will fill crucial gaps in our understanding of what the role the interface region plays in powering its dynamic million-degree atmosphere, called the corona. If you can please show my next graphic. IRIS will join the Solar Dynamics Observatory, or SDO, and Hinode. Together, they'll explore how the solar atmosphere works and how it impacts the Earth. Hinode and SDO looking at the surface of the sun and the upper corona, and IRIS looking at the region between. If you look in this movie, you'll see the full disk image as seen by SDO, the corona. Inserted are images of the photosphere and the chromosphere from Hinode. Iris will be the missing link between these two sets of observations. Now, to tell you the details about this, I'm pleased to introduce Dr. Untitled, the principal investigator for IRIS.
Thanks, Jeff. Just by happenstance, behind me, as a background, is a picture of IRIS, and it happens to be full size. So you can get an idea of the size of this mission. It's not a great, big, huge thing. If we could have the first slide. IRIS is the Interface Region Explorer. What is the interface? The interface is the place where the visible surface, the place where most of the light, or virtually all the light that leaves the sun, leaves from. It's about 6,000 degrees Kelvin, or about 1,000 degrees, 10,000 degrees Fahrenheit. Immediately above that, the temperature rises to the 1,000,000 degrees of the corona. How that happens is a mystery. What are the processes that occur there? What is IRIS going to do that's going to make a step forward? First of all, IRIS is about a factor of 10 higher resolution than any other instrument that has explored this region. And even more importantly, it's about a factor of 20 faster. So it can take images about once a second. This is critical because the processes that occur in this part of the atmosphere happen very, very fast. And I hope I can show you that in the next few minutes. But first, let's take a trip from the surface of the sun, which we can see now. That's the photosphere. We'll blend into the magnetic field, where black is magnetic field that's going out from the sun, white going back in. And the white lines are a simulation of what we think the magnetic field is. Above that, the upper photosphere, temperature goes up. Now we're into the transition region. We're going from photospheric type of light to coronal type light, where we can see sort of this iron filing picture, which we can compare with what we see in the magnetic fields. Now, I'd like to show you what we're going to try and target with IRIS. So if we can have that movie, on the top is the edge of the sun, and for context, that blue ball is the Earth. So you can see these structures are as long as the Earth. The panel below is enhanced, and these very fine lines are the jets that deliver the energy into the upper atmosphere. They look very small in this picture, but they're about 120 miles across, and they're about 10 to 50,000 miles long, and they travel at about 100 miles a second. So in a couple of minutes, one of those jets can travel around the whole Earth, and they're about the size of Los Angeles. So to get an idea of sort of a feeling, imagine an area the size of Los Angeles traveling around the world in 2 minutes. So if we have the next slide, this is a little bit more complicated region near a sunspot, and besides these jets, we can see the large plumes associated with the sunspots. And we'll show this twice because it's so pretty. Remember, these things are going 100 miles a second. Now we can also see these jets not only on the sun, but on the disk of the sun. So the next sequence will show a direct image and then an enhanced image. And you can see in the green enhanced image these fine spider-like web structures all over the disk. So these are the targets. This is what we want to understand. Now the problem that we have is that we really can't see this region. It's in light that's not visible, and the physics is very complicated. So there's been an international program to make synthetic images, and so the next sequence will show synthetic images of the sun. And we'll also pan across the image, and so you can see that these structures are highly three-dimensional. They're not in a plane, it's not a layer, it's columns of very rapidly evolving, rapidly expanding structures. Can we show that again, because it's so much fun? Okay. Can we show it again, please? No, you can't? Yes, you can. There, he's doing it. This simulation took about 3 million CPU hours on one of the largest computing systems in the world. Now, what I'd like to show you is not only do we have the simulation, but we can use this simulation to show what these jets are like. So if we can have the next sequence. And now you can see models of the jets. And the colors indicate temperatures. You can see the expanding plumes that we saw in the models. And if we can have the next sequence. This is another use of the simulation. Colors go from blue to red as the material heats. So we have models of how the heating process works in some detail. And these will be used to be compared with observations. They're not observations, and they may not be correct, but they're a starting point. So if we could go to this final couple of sequences, this is what IRIS does. Could we have the sequence? The yellow line corresponds to IRIS's spectrograph slit, and on the right-hand side of that is what the spectrum will see from that slit. And from those spectra, we can construct images over a range of heights, temperatures, and densities in the solar atmosphere. So that's what IRIS data will look like to the scientist on the ground. And then the final slide shows the comparison of IRIS with previous missions. IRIS is in the middle, and the two other missions are on the right and left, and you can see how much narrower the spectrograph slit is and how much faster it moves. And because of that, we can actually reconstruct the motions in these jets. And now I'll turn this over to Gary Kushner, who's had the enviable job of working with me and some of our scientists to actually build a thing that takes this kind of data.
Thank you, Alan. IRIS is a small, lightweight, low-power satellite designed to perform complex solar observations. IRIS is a NASA Small Explorer mission. We will fly in a sun-pointing polar orbit, about 660 kilometers in low Earth orbit. IRIS is the culmination of 3 years and about 9 months of effort by a team including people from Lockheed Martin, Smithsonian Astrophysical Observatory, Montana State University, University of Oslo, and with NASA Ames Research Center. On the first graphic, you'll see is a graphic of the observatory. The left, the orange area, is the spacecraft bus. The green and light blue area is the instrument. We'll talk a little bit about that more in a moment. It is about 7 feet in length and 4 feet in diameter at the spacecraft and 12 feet in width with the solar arrays deployed. On the next graphic, you can see this is an image of the actual observatory with the solar arrays deployed. This is in the clean room at Lockheed Martin. And in the next graphic, you can see it with the solar arrays stowed. This is in preparation for one of the environmental tests, vibration testing. In the next graphic, this is the instrument by itself. To the left of the white collar is the telescope assembly. To the right of the collar is the spectrograph assembly. And the white collar itself is a thermal radiator for the primary mirror, which sees the sun. This is the optical payload. And in the next series of images, they'll cycle through. This is the graphic of the payload with kind of the sides slowly cut away. And you'll see that if the sun is to the right, you'll see there that the red rays represent the telescope assembly. And that is the light being focused and projected onto the spectrograph, which is to the left of what you see as the green collar. And you'll see the blue and green rays. That's the spectrograph. And that breaks the light into its 4 channels, the far ultraviolet and near ultraviolet. And then that is put onto the CCDs, the cameras, and then projected down onto the Earth. On the next graphic,